Hi there and welcome from Ventura, California to today's webinar, On the Road to Autonomy, sponsored by Inside GNSS, Hexagon Positioning Intelligence, and Inside Unmanned Systems, hosted by WebAttract, the leader in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they discuss just how far we've traveled on the road to autonomy. You'll also have an opportunity to have your questions answered at the midpoint and at the end of the presentation during the Ask the Experts panel session with all of our panel members. Today we've invited you, as well as an audience of over 480 professionals registered across 52 countries, representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher Inside GNSS and Inside Unmanned Systems, would like to take a moment to welcome you and introduce our sponsor and moderator for today's session. Richard?
Thanks so much, Lori. On behalf of the Inside GNSS and Inside Unmanned Systems team, I'd like to extend a warm welcome to our international audience for today's web seminar. We're delighted you could all join us today. In just a few minutes, our panel of experts will provide what is essentially a virtual workshop on types of autonomous vehicle sensors, their integration, including regional and global corrections, as well as discussing navigation system integrity challenges. So in a very short time, they'll take us from the theoretical to the practical to the safety critical. Now, I'd like to introduce Natasha Ken Wong from our sponsor, Hexagon Position Intelligence. Natasha is a graduate of the University of Calgary's Geomatics Engineering program and joined Novotel, part of Hexagon's Positioning Intelligence Division, in 2012. There she worked with Novotel's SPAN, GNSS, INS products as an applications engineer and a product manager. Since the beginning of this year, she joined the Safety Critical Systems Group to focus on managing the automotive product portfolio. Welcome, Natasha.
Thanks, Richard. I just want to welcome everyone to the webinar and say on behalf of Hexagon Positioning Intelligence, we're really excited about the future of autonomy and the technologies that are emerging for autonomous driving applications. Novotel and recently acquired Autonomous Stuff are very much invested in resolving the challenges of research and development, precise positioning, safety and integrity, all for autonomous driving. And so today we've brought together a really diverse panel of experts to discuss their understanding and research on these topics. So I'm really looking forward to the discussion and questions from the audience. I hope by the end of this session that you guys will have developed an appreciation for the role that GNSS plays in reaching our ultimate goal of fully autonomous vehicles. So with that, I'll pass it back to you, Richard.
Thanks so much, Natasha. We appreciate those comments. Now I'd like to turn it over to today's moderator, Demos Gibre Egzieber. Over the years, Demos has helped develop and moderate many Inside GNSS and Inside Unmanned Systems webinars, and he's especially close and interested in today's topic. Demos is a professor of aerospace engineering and mechanics at the University of Minnesota. His research deals with the design of multi-sensor navigation and attitude determination systems for aerospace vehicles. Recently, his work is focused on multi-sensor solutions for operations in GNSS stressed and denied environments, including the use of such systems on unmanned and autonomous vehicles. Demos, it's always a pleasure. Welcome.
Thank you, Richard, and welcome everyone to today's webinar on autonomous systems. We're glad that you could join us. And before we get started and have our panelists present some of the very interesting and exciting work being done in this area, let's do a quick poll to get the pulse of the webinar audience. Lori, if you could pull up the first poll.
Absolutely. First poll on the screen. We'd like to hear from each of you. How critical do you think the GNSS component is compared to other autonomous driving sensors? For example, LiDAR, radar, camera, etc. Choices, as you can see on the screen: most important, very important, somewhat important, or not important at all. Give you a few moments there to vote. Okay, let's take a look at those responses. So it looks like we have 22% saying most important, 65% saying very important, 12% saying somewhat important, 1% saying not important at all. Demos, any thoughts on those responses?
That's a very interesting spread, and interesting to see that answer B got the most votes. Well, our panelists will make it clear what the importance of GNSS is in these autonomous systems as we move along with today's webinar. With that, let me go over and introduce our first panelist. Our first panelist is Terry Lamprecht. Terry started with Autonomous Stuff in 2014, the company's first application engineer. During his time with Autonomous Stuff, he has gained experience working with different sensing technologies and has worked remotely with customers integrating and troubleshooting autonomous systems. Terry is now Autonomous Stuff's Director of Products. He holds a Bachelor of Science degree in Mechanical Engineering from Bradley University. Terry?
Hello, everyone, and thanks for being here today. Again, my name is Terry Lamprecht, and I'm the Director of Products and New Technologies here at Autonomous Stuff. Before we begin, I'd like to provide you with a brief intro to our organization. Autonomous Stuff is a resource for finding components, software, platforms, and services that are used for autonomous development. Autonomous Stuff has provided more research development vehicles to this industry than any other provider. Our goal continues to be to help enable the future of autonomy and to accelerate our customers further towards their development goals. My role here requires working with both vendors and customers. We listen closely to the industry needs and try to find solutions that fill the gaps. Autonomous Stuff, as Tasha mentioned, is the newest part of the Hexagon PI family. We will continue working to provide the world's best solutions for both positioning intelligence and also automated driving. Today I would like to talk at a high level about the complexity of autonomous systems, the different sensor modalities used for automation, which sensor types are already in production, and which ones still have hurdles to overcome. This is all based off trends that we see from our customers working on development of different levels of autonomy and experience that we've gained while working with these different technologies. The image here shows a lot of the technologies that are commonly used for both ADAS applications and also higher levels of autonomy. Before we get too far, I'd like to give everyone a brief introduction into what I'm referring to as the levels of autonomy. This has been set out by SAE, kind of define the requirements for these different levels. Starting at level 0, we have no automation, so standard automobiles. As we move to level 1, we were talking about driver assistance or ADAS applications. So this can be things like adaptive cruise control, lane departure warning. Moving up to level 2, this would be partial automation. So autonomous emergency braking, for instance, falls into this category, as well as the Tesla autopilot system. Level 3 is even a higher level, requires much less interaction from the driver itself, but the driver still has to maintain awareness of what's going on and be ready to maintain or take back control of the vehicle at any time. And then we have this huge step function as we go to level 4 and level 5 that talks about the fail-safe operation of the vehicles. It requires little to no interaction from the drivers. But if the limits of the system have been met in or have been exceeded in level 4, the driver may have to take back control of the car. And then level 5 is what we all dream about. This is pulling the steering wheel from the car, sleeping while you're on your way to work, having the car pick you up from point A and taking you to point B, and doesn't even require a passenger in the car. The image you'll see on the screen here shows how complex many of these systems can be. But if you break these into smaller systems, it's basically ADAS features that kind of build upon each other to create these very intricate systems. You'll have short-range radars that are typically used for blind spot detection, rear collision warning, and cross-traffic alert. You'll have long-range radars that are typically used for seeing out many hundreds of meters in front of the car. You have ultrasonics that are primarily used for very short-range parking applications. LiDAR is probably one of the most intriguing. Can be used for a lot of different functions. But currently today's production sensors have only been used as a redundant source of information for other things like AEB, so typically coupled with a camera or a radar. And then lastly, cameras are used for a lot of different applications as well. They model the roads, tell us where it's okay to drive. They're the primary sensor for doing classification of obstacles. So briefly, I'd like to touch on the compute solutions that we see used. So you might ask, how do current developers work with data from all these different sensor types at the same time? Some customers use data loggers and hardware and loop type equipment, but for development, the trend that we typically see is for a industrial or ruggedized type computer to be used in parallel with the robot operating system, also commonly referred to as ROS. What is ROS? ROS is kind of a library of tools that allows you to not only abstract information from different sensors, but also to program the control of a robot, or in our case, a car. ROS also has a built-in visualization tool. You can see on the screen here. What this does is allows the user to kind of see what the sensors see. And also they can monitor the behavior of the algorithms that they've written. So they can see in real time kind of how the software is behaving and then make modifications to that. But before we get too much further, it looks like it's time for another poll. So I'm going to pass it back over to Lori.
Absolutely. I'm going to go ahead and put up our next poll, and we are going to request you on your honor system here, give us your top 2 responses to the following question. What do you think the biggest barrier is to widespread production of autonomous vehicles? Public safety, cost, regulation, infrastructure, or technology limitation? Looks like 65% public safety, 22 cost, 43 regulation, 27% infrastructure, and 30% technology limitations. Any thoughts there on these results?
I think that's in line kind of with what I see. I think public safety regulation will probably, in the long run, be the limiting factors. Technology is progressing so quickly that I doubt that even though we're hitting some struggles right now, I think that technology will overcome those limitations.
All right.
Okay, well, thanks, Lori. So the next thing I'd like to touch on is first of our sensors is radar. So radar has been used for production vehicles for over a decade. The applications, again, for this sensor include both forward collision warning as well as adaptive cruise control. We can also do blind spot monitoring. This is a sensor that provides very robust measurements. It works in adverse weather conditions such as fog, rain, snow. Again, these sensors are already being used and already meet automotive requirements. One of the trade-offs that we get from radar, though, is the resolution of the sensor. Also, the distance accuracy can be quite a bit less than we would see with a LiDAR, for instance. And then also, most current automotive radars are also 2D measurements. So we get a planar indication of where things are at around us. As we move towards 77 and 79 gigahertz units, the additional bandwidth there will allow expanded capabilities of these radars. Some of the new systems in development today also include vertical resolution, so we'll get more of a 3D snapshot of what's going on instead of just a single 2D measurement. Next up is LiDAR. Scanning LiDAR has also been around for about a decade, but typically only very simple systems have been used for production. And again, they're typically a redundant source of information as a check against a camera or a radar. As you can see on the screen here, LiDAR provides much higher resolution, 3D resolution. The black sensor on the screen is one of the first production-ready LiDAR sensors. So this will be going into planned level 3 cars in the very short future. This is the Scala from Valeo, and it's a 4-layer LiDAR that has a 145-degree horizontal opening. The LiDAR market continues to kind of wait for solid-state LiDAR and MEMS technology to really develop. The idea of having a more robust sensor that's not mechanical by nature embedded into more of the bumpers, the fascia, and the grille of the car is much more appealing than having a spinning mechanical LiDAR on top of the vehicle. So with that in mind, LiDAR manufacturers and the entire industry is trying to refine what that form and function of those LiDARs will look like And the price of these sensors is also a concern. So trying to drive down the cost of the very expensive components continues to be somewhat of a problem. The video on the screen here shows kind of how we make sense of some of the data from a laser scanner. So this is some software called LiDAR Object Processing, or LOP for short, from Autonomous Stuff. And what you'll see on the screen here is that we are doing a few things. We're starting off by segmenting out the ground layer. This is typically where it's okay to drive, and you'll see that as a red or brownish colored ring there. The next thing to do is to take a look at what resides above that ground layer. And then we look at those points, we cluster them together and track them over time. This allows us to do path planning algorithms, obstacle avoidance algorithms. The next step would be to take this and look at some of those tracks and make some assumptions about their size and their behaviors to actually give some level of confidence about the classification of those obstacles. So then we can actually tell whether or not we're looking at a pedestrian or a motorcyclist or a car. Next up for today are vision sensors. Camera technology is already very low cost. It's being used by almost every automotive manufacturer. It's great. Again, it's the primary sensor for doing classification of obstacles. Neural networks provide a very easy way to look at an object and tell if it's a car or a pedestrian. They're also very good for modeling the lanes of the road. So as you can see, the lines here lay out kind of where the road is going. And we can actually get an equation of the road that tells us what the curvature looks like ahead of us. One of the downsides to camera technology for developers is that the excessive amount of data that's required if you're going to collect this data, it takes huge storage capacity, and also computers can have quite a hard time processing raw image data from multiple sensors all at the same time. Manufacturers such as Mobileye, shown here on the left, have kind of mastered this process. They have taken and refined their algorithms and embedded them onto their own ASIC chip. So the camera does all the processing, and we just basically get back low bandwidth object data that we can use to make decisions off of. A couple of the downsides of camera are that they require proper illumination in order to see well. So overexposure and low light is difficult for cameras. They also require, they can't see better than we can see. So if the lane lines on the road are poor, we're going to have a hard time modeling the lane lines. So myself and others here at Autonomous Stuff believe that thermal vision will be used in parallel with visible cameras, and we'll be able to do things like pedestrian detection in the dark, actually allow us to extend that range during difficult driving conditions such as fog or smoke, and actually pick up information that can be used. So the combination of the two vision technologies together will be great. As we move towards more complicated sensing systems, it's going to be important to look at centralized processing. So some sensors do processing on their own, but as we move further and further, especially camera technology, will likely be processed on a central computer. The Drive AGX from NVIDIA that you see here, it incorporates some of their GPUs and provides somebody a place and libraries to use to perform some of this parallel processing that needs to be done. So this will enable advanced applications for 360-degree sensing, fusion, and advanced path planning algorithms. Very quickly, I want to touch on LVDS cameras. This is also used with the NVIDIA products, but these are lower cost sensors that operate over just a single coax connection to provide both high bandwidth data as well as power. We're all fairly familiar with ultrasonics. They're already low cost. They work well for short range applications, and they're a very good source of information for parking. And lastly, I want to touch on what we're here for today, which is GNSS systems. So what you see on the screen here is a span system from Novotel. This takes in not only GNSS information, but is also takes in inertial measurement information and wheel speed sensor information, and it kind of biases its overall positioning report based on how well these different sensors are picking up information. You'll also notice that there are a couple of antennas included here. This allows customers to very quickly get a heading information. And then we also look to RTK, or real-time kinematic updates, to take that positioning accuracy from a matter of a meter down to a couple of centimeters. One thing that's kind of worrisome is for RTK solutions to work everywhere, it's kind of unrealistic to assume that we'll be able to station base stations across the entire globe. And then the last thing here is PPP is also another correction option. It requires two-way communication with satellites and can take minutes to converge on a solution. So Lance and Samir will be talking about some of the advancements to these technologies that will make this a realization for the automotive industry moving forward. So thank you, Demos.
Right, thank you, Terry. All right. Before we launch into the next panelist, let's do a quick poll. Lori, if you could bring up the next poll.
Absolutely. On the screen, you've got the poll question. What level of positioning accuracy do you think autonomous driving requires? 0 to 10 centimeters, 10 to 50 centimeters, 50 centimeters to a meter, or greater than a meter? So looks like 44% with a 0 to 10, and 46% 10 to 50 centimeters, 9% 50 centimeters to a meter, and we've got a 1% greater than 1 meter. So any thoughts on these responses?
It's an interesting spread, and I think the next panelist will definitely address this one, and you'll see what the thought is in that areas today. So with that, let me move on and introduce our next panelist here. Our next panelist is Lance de Groot, who's a senior team lead of Geomatic Software of Safety Critical Systems. Lance de Groot holds a Bachelor of Science and a Master of Science in Geomatics Engineering from the University of Calgary. He joined Novotel, part of Hexagon's Positioning Intelligence Division, in 2008. During his tenure, he's worked on many cutting-edge technology projects, including developing algorithms for ground reference receivers using SBAS networks, high-precision positioning and relative alignment algorithms for commercial applications. His current focus is developing safety-critical software for autonomous applications. Lance is the senior team lead, Geomatic Software with Hexagon Positioning Intelligence Safety Critical System Group in Calgary, Canada. Lance?
Thanks, Demos, and hello to everyone in the audience. So I'll pick up more or less where Terry left off, talking about GNSS systems. But unlike the truth system that he showed you in the last slide of his presentation, I'll be focusing on production systems for production automotive. So GNSS systems in production automotive today tend to be an L1 only receiver. It provides a pseudo-range only position solution. And so that solution will have an accuracy on the order of several meters. And the use cases for this would be for the onboard navigation in the infotainment system, or possibly localization for emergency services. But the emerging applications we're seeing in terms of autonomous driving or ADAS applications are going to demand much higher accuracy. And so the industry is still settling on how much accuracy is required, and I think we saw that with the almost 50-50 split in that poll question between the bottom two levels there. So this is still being figured out, but we do have some indications of what the requirements will be. So for example, for vehicle-to-vehicle communications, there's a requirement of 1.5 meters at 1 sigma, and this comes from the NHTSA Notice of Proposed Rulemaking for V2V. And for true autonomous driving applications that require lane-level positioning, we expect an accuracy of something less than 1 meter. And you can derive this very easily just by looking at the standard lane width for a highway is about 3 meters. A vehicle will be 1.5 to 2 meters wide. So you have about 50 to 75 centimeters worth of error, margin for error there if you want to keep that vehicle within the lane. So we saw in the poll opinions ranging from 0 to 10 and up to 50 centimeters. So I think I agree with that in the sense of the overall autonomous driving application, including all of the sensor fusion. The GNSS component of that I would expect will be not contributing the full amount. So for GNSS, we're looking at a performance of essentially less than a meter all the time in what we're doing. So how do we get from where we are today to these new requirements? Well, there's two big things that we can use to get there. The first is that mass market chipsets that have dual or even multi-frequency have arrived. 3 of these have been announced in the last year. I would be not at all surprised to see another few announcements in the year to come. So that will allow us to use dual frequency measurements, which means we can correct for the ionospheric delay. We get some more observables. As well, we're seeing more constellations coming in with these new receivers. So that definitely helps. And then the other part of it, and this is where Novotel comes in, and Hexagon Positioning Intelligence with our corrections, is the high precision carrier phase positioning algorithms. So we can use algorithms that have historically been used in fields like survey or precision agriculture, and we can bring those to automotive to reach higher accuracies. So when I talk about high precision positioning with carrier phase, typically we're talking about 2 techniques, either RTK or PPP. So RTK works by differencing measurements between a fixed base station, or in the case of network RTK, a virtual base station, and the user. And by differencing the observations, you remove most of the errors, and that gives you a more accurate solution. RTK tends to be very regional. A network would cover maybe as high as the size of a US state or a small country. And the station spacing for RTK is about 20 to 50 kilometers. PPP works differently. Instead of differencing measurements, PPP works by providing corrections for all the errors that a user will experience. And then the user can apply those corrections to their solution to get a more accurate solution. So PPP, many of the error sources are global, and so you can have a global solution. So that these would be the satellite orbits, the satellite clocks, biases are all globally applicable. But you can also enhance PPP with regional networks to provide corrections for regional errors like the ionospheric delay or the tropospheric delay. Even a regional PPP network has a wider station spacing than RTK on the order of a few hundred kilometers. So this chart just summarizes the major error sources affecting GNSS and shows you which ones in RTK are just differenced out, anything marked with an X. So PPP, we have to account for everything. RTK, many of them difference out. So at Novotel and Hexagon, we believe that the right approach for automotive is PPP. And there's a few reasons for that. One is that there's one-way data transfer of the corrections to the user, whereas with network RTK, the user has to occasionally send their position back to the network for them to generate a new virtual base station. So because it's one way, it's automatically more scalable, and also you eliminate any privacy concerns with having to transmit the position of your users back to the service. The wider station spacing means less infrastructure, and also because you have a global solution, you're generating corrections in one place, and this is important for the safety of life concerns. I won't get into that too much in my talk. Samer will talk more about that later. But if we need to analyze the integrity of the corrections themselves, having one source of those corrections is an advantage. So what we're doing is we are focusing on using these new mass market chipsets with our PPP algorithms to try and achieve the requirements that are demanded by autonomous driving and ADAS applications. So what we've done is we've taken 4 mass market chipsets. 2 of these are L1 only chips that are in use in automotive today in some production vehicles. We also have a new L1 L2 chip from one of the same manufacturers, and we have an L1 L5 chip from a different manufacturer. And although it is dual frequency, the test corrections we used in this work are L1 only, so it's effectively acting as a single frequency chip. So you'll notice I haven't identified the manufacturers of any of these chips. And that's because some of these chipsets haven't been publicly released yet. They aren't on final iteration. So I don't want to present any results that are going to change before the chips get released. So you can consider the results I'll show you as essentially being representative of the class of chips rather than any specific receiver. So we start by looking at the measurement characteristics, because the measurement characteristics will inform what we expect to see in the position domain. And what we see when we compare this to a Novotel survey grade receiver is that the mass market chips have between 3 and 15 times as much noise on the pseudo-range measurements. And what this means is this is going to impact the PPP convergence performance. During convergence of PPP, we're effectively averaging the code noise in order to estimate the carrier ambiguity. And it also means these chips have a wider correlator spacing, which means more multipath. The phase noise is a little higher as well, but I don't expect that's going to be a big deal. We're adding a few millimeters of phase noise to a solution that has many centimeters of error, so it won't be significant. So we can see the impact of this in convergence. This shows over a number of simulated filter resets, on average, how long it takes to reach a certain amount of error in the solution. So you can see that all of the mass market chipsets have significantly longer convergence than a Novotel reference receiver does. And in particular, these chips, all the L1 only chips are never reaching this 1 meter level that we think we need to hit for autonomous driving. And even the dual frequency chip takes 9 minutes to get there. So this is, of course, not acceptable for automotive applications. A user is not going to start their car and then wait 9 minutes before their features are available. So this needs to be addressed. And we address this by our upcoming TerraStar X service. And what this is, it's the same as our global service with clocks and orbits, but it also includes regional ionospheric corrections. And by adding these ionospheric corrections, we can bring that convergence time down to, for most chipsets, we reach that 1 meter level in about 30 seconds. One chipset doesn't. That was the fourth one we tested. And it's also the one that has the highest code noise of them all. So you can see that the code noise does still have an impact even with the extra information. But I think this shows that this convergence performance is feasible for automotive applications. So in a minute, I'll show you some positioning performance from drive tests. But first, we're going to take a break for a bit of Q&A. And so I will hand it back to you, Demos.
All right. Thank you very much, Lance. All right. So we've got a few minutes here where we'll take a break and have questions from you from the audience come in for our panelists. So please send in your questions as we go through the Q&A here. All right. So to kick off here, our first question will be for you, Terry. And the question is, can you say something about the current practice of how sensor integration is done? That is, do the sensor OEMs do the fusing, or does the vehicle maker do that? And the question comes up because, again, at the low level of integration, different sensors have different informations on them that are not necessarily open to everyone to see. So, can you say something about that, Terry?
Yeah, absolutely. So, I mean, we see both sides of the coin on this. We have vendors or tier ones that provide sensors that have embedded tracking and fusion baked into them. But really what we're kind of seeing is a push towards more of that centralized processing that I talked about. So for instance, we used to see a lot more radars that came with tracking, and now they provide kind of just detection data. So they're expecting people to start developing these 360-degree applications and doing some of their own tracking at more of a global level. So it really depends. Things like Mobileye, I would assume that those cameras will continue to do some onboard processing. It's a lot easier to work with some of the low bandwidth data after it's gone through that than it would be to work with that on its own. So it's really kind of split, but the path that we're seeing is to start going more towards that centralized processing.
Okay. Anything that either Samer or I haven't introduced yet, but or Lance would like to add to that answer? All right.
I think I'd add just that I think there's a question of technology adoption here as well. So as these new technologies come out, the burden to attempt to try to do the sensor fusion all in one place while integrating the new technology is very high. And so in that case, it makes sense for getting sort of pre-processed outputs, as Terry was saying. I think as the technology matures more, that's where we'll start to see in which cases it makes sense to do the sensor fusion at a higher level and work on raw inputs instead.
Okay. All right. So while I've got you here, Lance, the next question is for you, and it's someone trying to understand something about PPP. The person says, I come from an agricultural background. Would PPP be similar to differential corrections that we currently use in agriculture? I guess it's a little bit of a tutorial type of a thing on PPP.
Sure. So maybe yes. Agriculture today, you might be using PPP already. A lot of agriculture is. A lot of agriculture has historically been using RTK. And as well, it's possible that you're using just differential pseudo-range corrections, which is essentially the same approach as RTK, but you don't use the carrier phase measurement. But you still difference the pseudo-ranges against a known base station to remove most of the errors. but I think maybe, so I don't know what you're using today, but I think probably what you're going to be using in the next decade or so, you will see the agriculture industry in general shift towards PPP because it's easier to service a wide area with PPP for the reasons that I mentioned.
All right. Thank you, Lance. Next question. I guess this one is for you, Terry. It's about the first, or I guess close to first slide that you showed about the different sensors on the vehicle. And it's that a compass was not shown. Are compasses used in autonomous vehicle navigation? If so, or if not, why not?
Yeah, I have no problem answering that. You know, we've seen very, very few requests from our customer base for a compass. It's something that I've dealt with a few times, but you know, I think that the general answer to this is that a system like SPAN that combines not only SPAN but their aligned solution as well provides a much higher resolution of heading than you would get from a compass, and also you don't have to worry about kind of magnetic anomalies that are taking place.
Okay. Let's see. Next question. This one is for you. Let's see, Lance. It's a question about multipath's impact on the PPP convergence time. It's just a general question: does that impact it, and if so, how?
It definitely does. So with multipath, it affects the code measurement much more strongly than the phase measurement. And so because the primary time that the code measurement matters in PPP is during that convergence period, also the primary time that multipath is a major factor is during that convergence period. So what we'll see if we do have a lot of multipath is that the convergence may take longer because we have more, effectively it's just adding a little bit of noise and error onto that code measurement. And we may also have biases from multipath that we need to be able to identify in the RAIM algorithms that we can remove at that time.
Okay. All right. For the sake of staying on schedule here, we'll cut this Q&A short here, but there's a second one coming in, and I see that there are a lot of questions coming in from our audience, so please keep that going. What I'm going to do here is I'm going to hand it over back to you, Lance, to continue on with your presentation. Lance? Before we do that. Yep.
Sorry, go ahead.
Sorry, it's yours, Lance.
Oh, okay. Thanks, Demos. So as I said, I'll show a little bit of kinematic performance results. So just a quick summary of our test setup. We take a prototype automotive grade antenna and we split that to the first 3 chipsets we tested. We didn't have a suitable setup for the 4th chipset in this work. And on the right side is a description of our truth system. It's very similar to the system Terry showed you earlier. It's a SPAN system that gives a centimeter level truth reference. So we did a few test drives. The first one here is a very benign environment. It's near the Calgary airport, so there's no high buildings because of the airport height restrictions. So it's a mix of some low buildings, warehouses. Actually, this road sign you see here on the top is probably the most terrifying feature of the entire route. So it's about as benign as an environment you can get inside a city without going straight out to rural roads. And so before I show you the results for the 3 chips we tested, I'll just show one version of this. And this is the difference you get from adding in our corrections and our high precision algorithms. So the red series here is the L1 only pseudo-range solution coming from chipset B. And the blue series is our corrected PPP solution. So you can see it does give us quite a large improvement, about 85% in this case. Across the 3 chips that we tested, it's about a 64 to 93% improvement. So definitely the high precision algorithms are doing a lot to help us reach these target accuracies. So this slide shows you the accuracy of the 3 chips tested in this route. So across the 3 chips, 95% horizontal error ranges from about 30 to 35 centimeters. So clearly this is viable now for ADAS applications or autonomous driving if we're aiming for that sort of 1 meter target for the GNSS system. So what happens if we make things a bit more challenging? So this is a route on the two main controlled access urban freeways in Calgary. So it's mostly open sky conditions, but it's punctuated by frequent overpasses. And these cause a total loss of lock. So we reset all the carrier phase ambiguities, and we need to have the filter reconverge each time this happens. So it's more challenging, but perhaps a more realistic scenario, especially for sort of highway assist systems that are some of the first ones I think we'll see. So if we look at the results, the 95% error increases, of course. We're now at about 71 centimeters to a meter. But you can see that the error is dominated now by sort of these large errors that happen every time we go under an overpass and the filter has to reconverge. So the filter does reconverge pretty quickly because of the ionosphere corrections. This shows the potential to integrate GNSS with other sensors, especially inertial navigation system here could help bridge some of those gaps, and we can get the accuracy down back to the level we saw before. So I don't have anything else to say about inertial in this presentation, but I think it is an important technology to sort of have synergy with GNSS the way it does in other industries as well. Then the last section I'll show you here is a more generally challenging environment. This is a residential drive. There's a lot of trees, foliage, sort of condominium buildings. So it doesn't have the total outages that the highway does, but it does have a more challenging environment, poor visibility of low elevation satellites. And what we see in an environment like this is, again, the error is higher than in the true open sky case. We're getting about 60 to 80 centimeters of error across the 3 chips tested. And sort of the steady state error is a bit higher than the highway because it never gets that nice open sky in between the outages. There's some potential here for inertial integration as well, but I think we're still within the viable range for GNSS to contribute to an ADAS system or an autonomous drive system. So the last topic I'd like to touch on before I finish up is just about antennas. So mass market chipsets have arrived. We're going to need mass market dual frequency antennas to use with them. And just like the chips, we would expect that the mass market antennas are going to have performance trade-offs that we don't see in the survey grade antennas that we have today. They'll have smaller elements, they'll have smaller ground planes, and so on. So what you see here is the L1 gain pattern of a couple antennas. On the left, one of Novatel's survey grade antennas, a 702GG, and on the right is our automotive grade prototype, the same one that we used in the testing I showed you just now. So there's 2 things I'd like to point out. One is that the roll-off in gain at low elevation is much more gradual on the automotive grade antenna. And so this means we're bringing in more power from signals at low elevation. So these are the signals that are most affected by the atmosphere, but this is also going to be ground reflected multipath signals. And the other thing to look at is that the gain in left-hand circular polarization, so these are reflected signals, is higher in general, which means that we're going to be bringing in more multipath power in general. So we can see that one of the differences with these antennas is going to be more multipath power. And we also saw earlier that these chips have wider correlators, so we think that the chips themselves are going to be more affected by multipath. So we can expect that multipath is going to be a bigger problem in these systems. And if we do a bit of testing in sort of moderate multipath environments, we can see this some of the time. So here's an example of a test. We parked our test van between 2 buildings. There's a building behind the fence here that's sort of hard to see. And then we split a automotive antenna and a mass market antenna, or sorry, a survey antenna and a mass market antenna to a survey receiver and a mass market receiver. And you can see blue here is the mass market receiver. The impact of feeding it with the mass market antenna is greater than the impact on the survey grade receiver, showing the compounding effect of that multipath. So this doesn't happen in every environment, and multipath can be very hard to predict and model, but I think it is a very important thing for the industry to consider when it designs these dual frequency antennas. So just to summarize, we believe that using these new mass market chipsets with Novatel's high precision algorithms and our TerraStar X corrections is a viable solution for bringing GNSS into autonomous driving. To get the convergence performance that we believe the industry will demand, ionosphere corrections are necessary. And lastly, the antenna performance is going to be very important, and we should consider this when we design antennas in this industry. And that's all I had. So back to you, Demos.
Thank you, Lance. All right, so before we move on to our last panelist, let's do another poll, if we will. Lori, can you bring up the next poll?
Sure thing. Got our 4th and final poll here, and the question is, in your opinion, what is the biggest risk to integrity? Interference, jamming and spoofing, data security, or GNSS measurement errors. Okay, looks like 30% with interference, 38% jamming and spoofing, 4% data security, 28% GNSS measurement errors. Thoughts on these responses?
All right, so looks like, well, not quite a tie, but a tie between interference and GNSS measurement errors, and jamming and spoofing gets the lion's share of the audience's vote. Well, our next panelist will address some of these issues, so let me go ahead and introduce our final panelist. And our final panelist is Dr. Samer Kanefsa. Dr. Kanefsa is currently a research assistant professor at Illinois Institute of Technology in Chicago and the co-founder and manager of TrueNav LLC. He received his PhD degree in aerospace engineering from IIT in 2008. He has been involved in several aviation applications such as autonomous airborne refueling of unmanned aerial vehicles, autonomous shipboard landing for unmanned combat air vehicles, and the JPALS program and ground-based augmentation system designs as well. His interests are on the high accuracy and high integrity navigation algorithms for close proximity applications, cycle ambiguity resolution, high integrity applications, fault monitoring, and robust estimation techniques. He's the associate editor for the IEEE Transactions on Aerospace and Electronic Systems and was the recipient of the 2011 Institute of Navigation Early Achievement Award for his outstanding contribution to the integrity of carrier phase navigation systems. Samer, with that, I will hand it over to you.
Thank you very much, Demos, for the kind introduction. So I think the audience for now have seen the hardware sensor components for autonomous systems with Terry, and Lance showed the current achievable precision of GNSS chipsets and how they can help autonomous systems. As an extension in my portion, I will touch on the safety of autonomous systems, which is, I think, part of the poll was addressing. So the motivation that we've been hearing about for autonomous driving has been the safety compared to manned driving. So the expectation is that autonomous driving will provide lower fatality rate. Currently, it is estimated that there is 1 fatality per 100 million miles driven, and this statistics has been computed based on several years. So with all the great work that has been done by different entities and groups, and I don't mean to minimize any of that work, just doesn't imply that autonomous systems should be allowed to be tested and then to count the fatality rate. Instead, there should be enough reliability already built into the safety of the autonomous driving system. So certain design requirements and safety standards with documentation of the system proof of safety should be made in front of certification entity. So you can think of it as just like a driving license. You just don't self-proclaim yourself to be a good driver and then just start driving on the streets. Instead, in the US, for example, DMV is the entity that provides the necessary tests to make sure that you are safe to drive on the streets. So that said, where one test might be enough for a human being, we all know as engineers that probably one test is not good enough for any computer system or even program. And therefore, it's not enough to demonstrate the system safety case through testings and demos only. They're definitely helpful, but that's not the only thing that we should be doing. There will be so many questions about the testing environment, the independence, where all scenarios considered, and how can we evaluate the likelihood of hazardous or catastrophic events beforehand for the design. So the system here is guidance, navigation, and control, and most of the presentation today I'm focusing on the navigation piece, but the same concepts can apply to the 3 components. So the answer to many of these questions, we propose borrowing from the concepts from the aviation industry in providing the design safety. The reason is because those were some of the common questions and concerns they had many years ago with different navigation systems, especially GNSS. So what they did in aviation is to define quantifiable system performance measures. That includes in addition to the accuracy, that includes integrity, continuity, and availability. Unfortunately, there will be no time to go into details about each one of these performance measures, But the idea is that a regulator entity puts requirements on these. So for aviation, it was the ICAO and the FAA. And the system designer or builder needs to provide a case proving that whatever system or design they come up with meets those requirements. So back to integrity risk here, in layman's term, it's a measure of how much can we trust the position provided by the navigation system. So that's going to be application dependent. It considers the risk of having a wrong position or fixed estimate. It also evaluates the likelihood of such a risk, including anomalous events. And I will explain more, hopefully, in the following slides. So this is a bit loaded slide here, but I will try to dive a little bit deeper into the concepts of integrity risk, which is I sub R in this equation, including its mathematical definition below and how it is related to the protection level, or PL. The requirements are usually provided as an alert limit, which is how much error the system can tolerate. So going back to one of Lance's slides, was showing about 50 to 75 centimeters as an example. So in the equation, for example, the system needs to show that the horizontal error is less than the alert limit with a likelihood that's less than the requirement. And let's say, for example, a 10 minus 6. So 10 minus 6 here means that you have 6 nines. It's 99.999% that you are sure you're inside your alert limit. Equivalently, in many aviation systems, they chose to transform this to the position domain such that they compute the protection level. So the protection level provides a statistical bound on the position error that can be computed if the distribution of the error can be found or inferred, known or bounded. And then make sure that this protection level is always less than the alert limit. So the system can be available if it meets these requirements. A hazardous misleading information event, therefore, are cases when this error is not bounded by the protection level. And remember that by design, you're supposed to always bound that protection level, but you're allowed only 1 out of 1,000,000 cases, which is 10 minus 6, to be outside those bounds. So in the picture below, the alert limit can be, for example here, the lane width, or half the lane width. In the first section of this scenario, if you look at the left over there, you notice that the errors, the position error is small, and the protection level also was small, and it provides kind of a measure that the likelihood of the error exceeding the green bound here is less than 10 minus 6. Now, even if this error increases due to noise, multipath, different scenarios, you would expect always the protection level to be inflated proportionally so that you are always bounding the actual error. Because if it doesn't, that's when you have an HMI event. And you can imagine that passing this estimate to a controller, for example, with an error that exceeds the protection level, where you think you're trusting the system up to the 10 minus 6 level, while it was not, it could be catastrophic. So these events could happen due to several reasons, but they need to be mitigated, as we will see in the next slides. The other nice feature about the protection levels is that they have the capability to kind of predict in the future what the system, how the system would behave given a proper design. So you can always compute what the protection level would be, and therefore if you predict a case where it will exceed the alert limit, you may warn the user, or for example in this case provide enough time or warning before disengaging the system. So now let's dive a little bit into the key aspects of the integrity risk. So in designing a high integrity system, you need to analyze and address every system node for threats or faults. So you construct a fault tree or integrity risk tree. Each threat or fault needs a threat model, meaning you need to know its likelihood of happening, its magnitude, its profile, how does it impact the measurements, and how would that carry on to affect the position, etc. Once a threat model is identified or defined, a threat mitigation scheme can then be developed to guarantee the integrity risk. So some of the techniques used can be detection, sometimes monitoring, error bounding. There's so many different techniques in the literature. Notice that the threat model itself and mitigation techniques are not one fit all. They depend on the position system. So example, they might be different for differential GPS or RTK systems than PPP, etc. So for example, for GNSS, we can look at every possible fault from the signal generation all the way to the position estimation. So this is an example of threat models that can be identified for GNSS. So starting from the satellite, the signal may have deformation anomalies. It could have clock faults or orbit parameter faults. And just a reminder, all these faults have actually happened in the past. So all these collectively are referred to as satellite faults. When the signal travels through the ionosphere and the troposphere, anomalies in the shape of ionofronts, storms, or scintillation, and tropospheric ducts or weather fronts need to be addressed and mitigated. On the ground level, interference in the shape of jamming or spoofing also need to be mitigated, and so is the case with excessive multipath. And I think all these three were kind of closed, equally addressed as part of the high risk for GNSS. So the analysis goes all the way down to the user equipment itself. The likelihood of receiver faults can be manifested in anomalous data on single or multiple channels. But the good thing here is that what the aviation community has accomplished over the years is that they developed threat models and research to provide several mitigation techniques to many of these issues that may guarantee the navigation safety or integrity risk. So one of the common mitigation techniques or approaches is developing a monitor to detect the fault in any specific node. In designing the monitor, you utilize the threat model that has been defined, the physics of the threat itself, and any redundancy available. Example, the many satellites available, or you might have different sensors that help you in mitigation and detection if there's any fault in these systems. After detection and depending on the requirement, the system may have to identify the fault and exclude it. And in some cases, after exclusion, you need to have a recovery logic. And in both cases, also, you got to be careful and pay attention to the likelihood of wrong exclusion and early recovery. But in general, though, systems shouldn't be judged based on accuracy only. In fact, in many cases that we looked at, a navigation system that's tuned to provide the highest precision or accuracy does not necessarily translate to high integrity. In many cases, we actually saw the opposite. Or in some other cases that when we analyze the system, we found that it's so complex and fine-tuned around extracting the most accuracy to the point that evaluating a meaningful integrity risk or probability becomes infeasible. So the trick in those cases is to find this balance between having enough accuracy while at the same time being able to provide and guarantee the integrity risk. So for example, fine-tuning the estimated parameters to get high accuracy results for experiments is not considered an advisable approach from an integrity perspective. Instead, you may use the data itself that's collected in a different way, and I will show you just a simple example in the next slide. So here's kind of a favor of how we approach data. And again, this is just an example. There are different ways you can use the data and different techniques. So take the multipath error, for example. In evaluating the integrity risk for autonomous vehicle approaches, it's important to provide conservative error models, meaning overbounding from stochastic point of view. And autonomous systems or GNSS systems need to account for multipath because it can occur due to signage, overpasses, trucks, etc. And I think you've seen some of the pictures that Lance provided. The approach we proposed in a previous paper that's referenced at the bottom there is to bound the error under driving conditions or environment, and in this case without using other systems to detect it. As I said, this is just an example, one way of using it. What we provided in that work is to provide GNSS error models under conditions representative of automotive environment. So that was intended for navigation integrity and continuity evaluation. We provided error models that cover multi-frequency, multi-constellation, code and carrier phase GNSS measurements under both static and dynamic multipath environments. And we characterize the errors by the mean and standard deviation of a bounding Gaussian distribution, in addition to the autocorrelation time constants of the measurement error. So now going back to how we use the data. I will start here with a little bit of theoretical mathematical work on the CDF bounding that was done by the aviation research community decades ago. And bear with me here, it's a bit loaded mathematical definition in the bullet there, so I'm not going to repeat it. I hope you will read it. But I will try to summarize it in a couple words. So what that definition is saying is that if you can bound the error on the measurements themselves, the distribution of the error, by a Gaussian distribution with a certain mean and standard deviation, you may derive a protection level that is guaranteed to bound the actual estimate error from a stochastic point of view. And remember, that was the goal that we wanted for the protection level. So in the example of the chart on the right-hand side, the blue curve there represents empirical values for the multipath errors that were collected under certain data collection campaign. And if you just compute the standard deviation and mean of this collected data, which might be commonly done to kind of come up with an error model for the multipath, the distribution will look like the light blue curve over there. So the theory that I just referenced state that because the likelihood of certain error magnitudes, take a 2 meter for example, exceeds that from a Gaussian in light blue, it is likely that the actual estimate error that you will use using this standard deviation, the actual error is going to exceed the protection level that we will compute using your estimator. However, if the sigma or the standard deviation is inflated for this data or for the multipath such that it bounds in a probability or CDF sense the empirical multipath error, then the protection level that you may compute from your estimator is guaranteed to bound the actual estimate error. And this is the approach that we, with Novatel's collaboration, have decided to follow for certain multipath errors. So we're running data campaigns with the goal of providing bounding error models for automotive environment. So in summary, I wanted to remind you that the integrity of GNSS has been scrutinized like no other sensor systems that I am aware of. And it had, the reason for that is that it had to go through brutal certification procedures by the FAA and the ICAO because it has been proposed as a replacement for current systems in terminal approach and landing phases of a civil aircraft. So what we did is we presented some of the approaches of guaranteeing integrity risk or the safety of navigation system for GNSS, but the takeaway here is to apply the lessons learned in aviation to autonomous driving field. If we apply the same scrutiny and rigor to other navigation systems, we will find that those will make those more robust and less functional tuning parameters. An example is spoofing that you guys responded to in the GNSS poll. But if you search for full in computer vision, you'll find so many work that is being done there with not much mitigation that I'm aware of. And the last two bullets just kind of summarize where we are at Illinois Institute of Technology and at TrueNav. And I will, without repeating those bullets, I'll just leave the slide there and I'll get back to you, Demos.
All right, thank you, Samer. All right, so before we head on to our last Q&A session here, a couple of things about moving forward. So this chart provides some contact information if you want to find more information on what was presented today by our panelists. So with that, we will move on to our last Q&A portion of today's webinar. All right, and thank you, by the way, our audience for sending in lots and lots of questions. We may not be able to get all of them, but we will try our best. All right, with that said, let me start out with the first one. This one I'll address to you, Terry, and Lance and Samer, you could chime in after Terry comments on this. And it's kind of a open-ended question in the sense of how soon can we expect autonomous vehicles to be implemented?
Okay, well that's a great question. So it's really hard to put a finger on that. What we're seeing right now is some of the most advanced development is being done with companies that are more likely to implement ride sharing than necessarily to sell vehicles to the general public. So I'd kind of like to talk about it a little bit and just say we see that there will be a shift. And there's data to back this up that people are moving towards this rideshare economy as opposed to owning their own vehicles. It's not necessarily something that I look forward to. I like to have my own car. So I kind of hope that this doesn't come true, but at the same point, we really feel that in the near future, we'll start to see more and more shuttle type applications and ride sharing services developed before we see regular automobiles ready. And I'll kind of point that over to Lance and Samir and see what they have to say as well.
Yeah. Any inputs, Lance and Samir? Anything you want to add to that?
I guess I'll add a bit from the perspective of the traditional automotive manufacturers. I think there's a lot of activity right now sort of pushing that level 3 level of autonomy that Terry showed in his slides. And so I think that's where we're going to see not full autonomous cars, but we're going to see sort of near autonomy, advanced ADAS features coming probably within the next 5 to 6 years from most major manufacturers. As to when we get to level 5, on that front, I'm not sure when that will be. It'll be a little while still.
Right. Samer, anything you want to add to that?
I think I will add to both what Lance and Terry said is that some of the issues that I personally see with even with level 3 is that even the safety of some of these features, additional features on cars, may have not been properly demonstrated. So moving from that to level 4 or 5, I'm not sure. I don't mean to sound pessimistic, but I think the safety component of the designs may have not been properly demonstrated yet. That's my opinion.
Okay. Thank you. All right. This next one is for you, Lance. And the question is, will dual frequency chips eliminate the need for broadcast ionosphere corrections mentioned in your presentation?
Okay. I think the ionosphere corrections will definitely still be required. I won't try and page back to the slides, but for the L1L2 chip we tested, it brought the convergence time to get to 1 meter down from 9 minutes to 30 seconds, adding those corrections even to dual frequency. So they are very important. And in fact, the single frequency chips and the dual frequency chips all had pretty similar performance with those corrections. So that's not to say that the other side is true, that if we have the corrections, we don't need dual frequency. I think we do still need that. More information, of course, is always better. As the ionosphere gets more active, we can expect that the corrections will be start to have a little bit more error in them. And from an integrity standpoint, having 2 independent sources of that information is always valuable.
Okay. All right. Next question. This one is for you, Samer. And it's the question is, can you comment on how aviation approaches to integrity can be adopted for autonomous safety cases where GNSS is integrated with other sensors, like LiDAR and vision systems, to maintain performance-degraded environments. So, for example, multi-faults are generally present in vision systems, but that's not necessarily, I guess, considered in prior approaches. So, can you say something about that?
It's that's a very good question, and I think but I'm really happy to see that this is an active area of research. So although it's not mature enough to provide high level of integrity, but I'm aware of a few people in the research community who are working to try address this issue specifically. So there's work of using vision systems or other sensors to kind of provide integrity for GNSS, and at the same time, I'm aware of other work that's trying to use the sensor fusion to kind of provide a high level of integrity. But as I said, it's not fully mature yet, but there are certain people who are working on this field that hopefully in a few years we might have a full answer for it.
Okay. Lance or Terry, anything you'd like to add to that, or?
I think Samir did a very good job.
All right.
Agreed.
All right. Next question. This one is for you, Terry. And the question is ROSP currently being used in production vehicles? If not, is it really a valid solution for automotive applications outside of the R&D domain?
Okay. Yep. So during my talk, I mentioned that this is what we see in the development realm. Standard ROS that most folks know today, I highly doubt would ever be used in a production environment. ROS is coming out with a new version called ROS 2 that's intended for automotive applications. It's hard to tell at this point whether or not that will make it all the way down to embedded systems for production vehicles. But the current state of ROS today, it is a development tool, in my opinion.
Okay. Let's see. Next one here is, this one is for you. Let's see. Oh, right. Well, questions are flying in, so apologies here if I'm not keeping on top of them. All right, so this one is for you, Samir. It's kind of a general question, kind of open-ended. It's how do we predict errors in autonomous systems? I think you addressed it a little bit about this in your slides, but can you say a little bit more about that?
This is a very difficult question to answer because it's a whole research area. So I would say yes, part of it is in my slides, but there's so much details that I'm not sure even the time would allow for that. But yeah, and in general, it's what I presented about.
Okay. All right. Next question. This one is for you, Lance. Other than initial convergence times of a couple of minutes with what you've shown, what are the reconvergence times after satellite for TerraStar? What are the reconvergence times after satellite loses lock in an urban area?
Okay. So for a short outage, we'd expect reconvergence times to be on the order of maybe 10 to 20 seconds to get back to the previous level. And the difference there is that during initial convergence, we do still have to estimate the ionosphere a little bit, but from a short outage, we can carry forward the existing estimates of that with some degradation.
Okay. Let's see. Next one for you, Terry. And this one is, are there some proposed alternatives to GNSS in GNSS-denied environments like tunnels, urban canyons, underground that are being considered? And I think you did address this a little bit, but can you say more about that?
Yeah, sure. So GNSS is not the only positioning solution out there. I would say it's by far the most mature and the most reliable. But we have customers day in, day out that are looking at things like SLAM with both cameras and LiDARs that can map the environment and then localize to it. The downside there is that you do have to map your entire environment that you plan to drive in beforehand. Also, radio technology can be used, ultra-wideband it can be used to provide some positioning updates as well. So I think in the end, we're going to look at, coupling in SLAM or ultra-wideband or localization based off of lane lines or objects that are out in the world, along with the GNSS type positioning engine in order to get a redundant, reliable solution.
All right, Samir and Lance, do you want to add anything to that?
I think I would just add that there's the potential there to leverage some synergies between GNSS and the other technologies. So, for example, if you're entering a GNSS denied environment, going into that area, GNSS would, of course, have a good position, and so maybe that can be used to initialize something like a SLAM algorithm rather than forcing it to basically start itself up. And likewise, you could hand off the other way on the way out again.
Okay. Samer, anything you want to add to that?
I think it also depends on how these sensors are integrated. So if they're integrated at the measurement level, then we got to be careful of also how the integrity risk is quantified there. So for example, I'm aware of many problems with SLAM algorithms when it comes to integrity because of misassociation and in some cases even misclassification of a feature. So I think integrating these together is very helpful. It's definitely is the way to go maybe in the future. But again, I don't believe it's mature enough to provide an integrity yet.
Right. Let's see. All right. So next one is for you, Samer, and I guess Terry and Lance could also chime in afterwards. It's about the algorithms used in autonomous systems. I mean, a lot of the work that's been done with integrity has been for GNSS type of applications where softwares are, snapshot type of solutions. When you have deeply integrated sensors and recursive filters, how is all of that going to work from an integrity point of view? Can you is that something that's being addressed? Is that something you could say something about?
Very good point. Yes, so I agree that most past aviation systems that I've been referring to in my slides were for snapshot systems, and more recently, or even other non-autonomous driving necessarily, more system has been relying on filter techniques, for example, Kalman filtering, and it's an active area of research, definitely. We are currently working on it at both Illinois State Technology and TrueNav, but there's no answer that fits all. An example is usually time correlation is handled in a very simplistic way with snapshot systems. Once you talk about Kalman filtering, time correlation is the nature there of it and its impact on the integrity risk is something that's not easily quantifiable, although there are methods that we have developed in the past. In addition, with filtering techniques is that sometimes if you haven't detected the fault right now, but the fault was existent in the past, you have always to think of, well, let's say that you detected a fault at this moment. How do you know that this hasn't been in your filter for some time? And if you think of a GPS IMU, how do you know that that fault didn't even corrupt your integrated solution? So as I said, this is a very active area of research that I personally am interested in and working on. We have some solutions for certain cases, but as I said, it's very case dependent.
Okay. Lance or Terry, anything you'd like to add to that?
I think I'd just add that from my perspective, this is one of the two big steps that need to be made to take the aviation techniques into the automotive domain. The other one being that we have a different environment, so especially multipath errors and spoofing errors are different.
All right. All right. Let's see. Next one. Well, this one is for you, Lance. Again, there are a lot of questions that have come in that have the same flavor to this. So I'll use this one as a wrap all for all of them. Is it safe to say that the days of RTK are numbered in view of PPP coming online?
Sure. I don't think I'd put the nail in RTK's coffin just yet. I think there will always be applications for RTK, especially in areas where the use is in a very constrained area, so like construction survey, for example, is an excellent application for RTK where you can set up a single base station and service your entire application. I do think that PPP is going to take over some of the industries like precision agriculture, which have historically used RTK, but now that the performance of PPP is approaching the levels of RTK with the addition of ionosphere corrections, and it's because it's much easier to service a wide area with PPP, I do think we're going to see it take over in industries like that. And I think automotive is another example of a case where it's suited.
Okay. Samer or Terry, anything you want to add to that?
I think I agree with Lance. It's not that it's going to take it completely. It's going to take maybe a big portion of the RTK business, but there's still few that might benefit from RTK as is, especially if you're talking about local application where you don't necessarily need the global corrections, but you're more interested in much higher precision, such as structural monitoring is one of these examples. So in those cases, if you're talking about even sub-centimeter or centimeter accuracy, probably PPP might not be there. But again, I mean, it's going to reduce the market for RTK. It's my opinion.
All right. Terry, anything you want to add to that, or?
No, I concur.
All right. All right. Well, next one, I'll direct it at you, Terry, first, but I think Lance and Samri could also chime in after he does. Is there a preferred location for installing an IMU in this big sensor suite of mix on cars, autonomous vehicles, rather?
Sure. Yeah. So, one of the most important things is that we have a very rigid body surface on the vehicle to mount the IMU. So we work with systems from Novotel that have integrated IMUs into the receiver itself. But on the higher end systems that have standalone IMUs, typically we are trying to mount those as rigidly as possible directly above the rear axle, the center of the rear axle of the car. And it basically just makes the transformations a little bit easier to deal with, from a setup and integration point of view, if we can position it at that point.
Samer, and with respect to integrating, do you see anything you want to add to that as to location of IMUs relative to GPS, et cetera, antennas, and so on?
Yeah, I agree with Terry that you want that to be as rigid as possible to reduce the errors in the integration. You don't want too much vibration, and at the same time, you don't want any the lever arm between the IMU and the GPS antenna needs to be known precisely, and therefore, if there's any chance of that changing with time, that's going to introduce errors. So the ideal location, of course, is to have the IMU and the antenna together at the same location, and to have that in a rigid place. But again, it's application dependent. So if that's not feasible, you try to put it as close as possible, surveyed precisely with respect to the antenna and in a rigid location.
All right. Let's see. So one more question here, and I think we might be running out of time. And I guess several questions have come up. They have this same flavor, so I'll ask it just one of them and see if we could catch all of the dimensions of that problem. And it's basically, do you see any, and this one is for you, Lance, do you see any use for information exchange, crowdsourcing, et cetera, with vehicles to deal and mitigate with some of the GNSS errors in these applications?
I do think there is some potential there. So this is very similar to the approach of V2V, where vehicles can transmit information about their position to each other. You could also have vehicles transmitting other information to each other that would help. I do think there is a concern there in terms of the integrity of that information, and maybe Samer will have some comments on this as well. But if you are getting your information only from a correction service or from SBS, for example, or from the satellites themselves, it's very well controlled. But if you're taking the information from other users, the potential faults there are much higher.
Yeah, this is Samer here. So I completely agree with Lance there. So the integrity of this information is going to be a key aspect there, is how much you can trust that information. So if this is all enclosed in one system, that's one way, of course, that you could, if it's controlled. The other thing is, if you think of kind of data campaigns, kind of crowdsourcing, so similar to the work that we've done in the reference that I showed in my presentation. If you think of multiple users collecting data and then providing this to a certain repository to analyze multipath, it definitely helps. It helps a lot in building the error models for different environments. And it's actually one of the things that we thought of when we started working with Novotel. But let me talk here about multipath specifically. The tricky part there is that multipath is not necessarily only from static or rigid structures. You might be driving on a highway near trucks, and that truck will introduce large multipath that if you just completely rely on the data that you have, you'll find yourself vulnerable to these errors that you didn't even think that they exist at that moment. So it helps, but at the same time, you always have to account for anything that this data doesn't provide in the environment, or that the environment may change, which if you think about it, it might also put less weight as people may have think of, oh, we have all this data. We're pretty sure that we can come up with accurate models.
All right. Thanks, Emmer, and thanks to all our panelists. Unfortunately, we are just at the end of our allotted time, so we're going to have to call it quits at this point. So I will hand it over to Lori and to close up this webinar. Lori?
All right. Thanks, Demos. And before we do sign off, folks, I'd like to thank each of you for joining us. Trust that you found today to be of value. Very special thanks to our distinguished panel members and, of course, our sponsor, Hexagon Positioning Intelligence, and co-hosts Inside GNSS and Inside Unmanned Systems. Most importantly, thanks for joining us. This is Lori Dearman saying hope we see you on the next one. Bye for now.